Uh, Good day, grade 12 learners. And today we are starting with physics revisions. We are gonna be doing the motion, specifically the graphs of motion. And you'll find most of these graphs in question number 3, where you have to tackle the projectile motion questions. So we are going to be taking 3 scenarios whereby the question you will find in question number 3 in your final exam paper will contain. Let's read here. Let's look at scenario number 1. We have a released mass. We have this boy here standing at the top of a 70-meter building. He's holding a ball, and okay, let's read it. A ball drops a stone from the top of a 70-meter building. We have a boy here. This boy drops or release. What you see with like drops and release, just note that the initial velocity or VI or V initial is 0. Just be aware of that. And okay, from the top of a 70-meter building, as the diagram below illustrates, we can see here we have a 70-meter building. We have a boy standing at the top. The boy releases or drops a ball, and when the boy drops a ball, what do you think is going to happen to this stone, not ball? What do you think is going to happen to the stone? The stone, of course, will experience free fall. It will experience free fall. It will fall until it comes to rest on the ground. Of course, it will strike the ground with a certain velocity. We don't know that velocity, but we can calculate it. But in this video, I want to make it short and simple. We will only look at the graphs of motion, and we will do the calculations later. And how I'll show you how to answer questions based on the graphs of motion. And yes, the boy is going to release the ball. The ball will experience a free fall. Remember that a free fall is the motion of an object where the only significant force acting is the force of gravity or the gravitational force, or we may call it the weight, however you want it. First of all, let's look at the velocity time graph of this of the motion of this ball. Why do I keep saying ball? Of the stone, man. Let's look at the velocity time graph of the stone from the time it is released until it hits the ground here. Oh, before I forget, you have the choice of choosing your direction. It's either you choose upwards as positive or you choose downwards here as positive. Let's look at when you choose upwards as positive. We know that gravity always acts downwards. Even if you choose your direction to be upwards or downwards or left, right, it doesn't matter, but gravity always acts downwards. And here in red, the red line here represents when you choose upwards as your positive direction. You choose upwards as your positive direction, but what happens to the velocity of the stone here? Of course, the velocity of the stone will go opposite to your choice of direction. In this case, it will experience negative velocity here. It will experience negative velocity until it comes to the ground at time x here. And if you choose downwards as positive, what happens to your velocity? You choose downwards as positive, your velocity is going downwards. That means your velocity is in the positive, the positive is going to the positive according to a direction. Let me say that. Yeah. That's why the graph here, it has a positive slope. Remember that the slope or the gradient of this line represents a acceleration due to gravity. Gradient is change in y over change in x. And remember that your change in y is change in velocity over change in time. What does this equation remind you? It reminds you of this here, change in velocity over change in time. It reminds you of what? Acceleration. But here we're talking about acceleration due to gravity. And the area under this line here, it represents the displacement of your your projectile here. We know that the area of a triangle is equals to half base times height. In this case, we have what is our base here? Our base is time. You can say t. Our height is what? Is velocity. You can say velocity. What does time times velocity remind you of? Of course, it reminds you of the distance. If you remember the grade 10 formula here, which says distance is equals to speed times time. Here the time here times the speed here will give you the displacement. And yeah, I think we talked enough about the velocity time graph. Of course, it represents the initial velocity of the stone from the moment it is released until it hits the ground here. And of course, it's a straight line. It's a straight line graph. Someone might ask, why is it like a straight line? Remember that in mathematics, a straight line is given by y is equals to mx plus c. Here, if you look in your data sheet, we are given this equation here is equals to v initial plus change in time. We know that the velocity here, I can write this equation in a different form, but look at this: change in time plus v initial. Let's compare this equation and this equation right here. We have mx. M here represents the gradient. G here represents the gradient, which is the gravitational acceleration. T here represents the x here. You can see the c constant here represents this constant here, which is the velocity initial. That's why we have this graph here as a straight line. I hope you understand. Let's move to another type of graph, which is we have here the position time graph. We have the okay. I'm just coming back from school now. Hey, I'm very tired, but let's get on with it. The position time graph here. You have a stone released here. It goes down, 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 down until it reaches the ground here. And when it reaches the ground, like the choice of your direction, if you choose upwards as positive or if you choose downwards as positive, it's going to affect how your graph will look. Here, let's see if we choose upwards as positive. Remember that let me show you something real quick. In mathematics, the graph of parabola, not hyperbola, is given by ax squared plus bx plus c. If here a is positive, your graph will look more or less like this. But if your is negative, if your a value is negative, your graph will look more or less like this, going down, down. Back to the position time graph, we choose upwards as positive. If you choose upwards as positive, but the displacement, the stone is going downwards, that means your gravitational acceleration will be a minus 9.8, because no matter which direction you choose, gravity will always act downwards. Okay, if we have like we choose upwards as positive, our gradient is, why am I saying gradient? Your a value here is minus 9.8. Your graph of course will look like this, here. And even if you choose downwards as positive, your graph here will look like this. It all depends on your direction. If you choose downwards as positive, your graph here will be like this. And I think that's it about the position time graph for this scenario here. Like, if you don't understand the position time graph or the velocity time graph, you can just inbox me on WhatsApp and tell me where you don't understand, and I will try to explain fully. And the last type of graph, the easiest one, we have the acceleration time graph. You choose upwards as positive, gravity act downwards, so your graph will be here on minus 9.8. It will always be constant. It does not change, it does not move, it will always be constant. And here you choose downwards as positive, and your acceleration is also going there. You see, it's always downwards, and your displacement is also downwards. That's why we have a positive 9.8 here. And like I said in the beginning, your choice of direction will determine how your graph will look. If you choose upwards as positive, or if you choose downwards as positive, your graphs won't be the same. And I think that's it about the scenario number 1. But let's look here. Why is this a parabola? Like, why is the shape like a parabola? Remember, on your formula sheet you will get an equation that looks like this. Changing y, yeah, I think it's changing t plus half g changing t squared. Let's compare this. You have ax squared, you have half g t squared, you have bx, you have here, you can take this as bx, you have your constant here c, you can take this one here as c as your constant. And that's why here we have a graph that looks like a parabola. And let's go through scenario number 2, but I will do this in a different video, and I think I will see you in the next video.